Right, there we go. Okay.
Hello all. Well, this week you're going to be presenting your research that you've been working on all term to the class. I also had an assignment for this week, and that was to answer all of your questions that have not been answered so far from the general knowledge background quiz from 8 weeks ago now. My hope is to give you a model about how you might best do these sorts of presentations. Giving a presentation is an art. It's a performance, not unlike a rock band. Try to think about what's good about the presentations you enjoy and what you don't like about the presentations you don't enjoy, and incorporate those into yours. The best way to get good at it is to do it again and again and again and again. And the more presentations you give, before long, it becomes second nature. So, on to the questions. Let's see what we can learn about space this week. All right, well, the first one, a couple of you actually asked about black holes and possibly wormholes. Well, we covered this in week 2 already, so I'm not going to spend too much on this. You know, largest stars with so much mass that even the nuclear forces inside the nucleus of the atom cannot withstand the gravitational collapse, and all matter is crushed into a singularity, a proverbial point, with a ridiculous mass large enough even to stop the emission of photons from moving. Well, maybe that's not true. It's definitely gravity strong enough to bend light around. That's probably more accurate. Initially, black stars were suggested by English clergyman John Michell in 1784, like we talked about. Scientific community was all abuzz, searching for these invisible stars. But once it was determined that light acts as a wave as well as a corpuscle, the idea fell out of fashion. But gravity does impact the motion of light. So in this letter here, this is where you can find the original letter that John Michell wrote. It would not be until 2019, just 2 years ago, that the first ever image of a black hole was taken, and this is what we're looking at. It's actually false color because the image that we're seeing is visible only in X-rays. As we discussed in week 2, spectroscopy came into astronomy in the mid to late 1800s and showed us the temperature and even the composition of distant stars. These discoveries continue unabated today, growing in parallel with developments in optics and sensor technologies as we are able to see further and further with higher and higher resolutions. But you have to keep focused on the same part of the sky long enough to take that sort of an image. So the image that we saw on the previous screen, it actually took all of these different astronomy observatories around the world simultaneously going back and forth so that they could stay focused on the same spot. Pictured in the background here is the large Atacama millimeter array in Chile, which was one of them. One last thing. In the first Cosmos remake by Neil Tyson, he suggested that each black hole singularity could in fact be its own Big Bang, creating a whole new inflating universe on the other side. They would never know about us, and we would never know about them. Some have suggested it could create a wormhole, perhaps a rip in our universe that reemerges somewhere else within our universe, or perhaps somewhere else. It's all possible. It is. But just like many other mysteries, there's a lot of theory, but no real way to know. We can barely keep a probe alive on the surface of Venus for a day, let alone go through a black hole. And if if the ship somehow survived, it would never be able to send the information back to us. Typically, most people looking into this are looking for a shortcut, a way to get from here to there in a nice, easy, quick way that saves us a whole lot of work. Well, if there's one thing I have learned from my work on space, is that there is no such thing as the easy way. You either work at it until you're done, no matter how long it takes, and you get it, or you don't. Neither decision is right and wrong, they both just are. But there is no easy way, it's always the hard way. For more on black holes, you'll need a different sort of class, I'm sorry to say, and someone perhaps a lot smarter than me. Well, here's a good place to start. There's a thing there, and it's also a pretty good Disney movie. So the next question was, are sci-fi movies getting our hopes up? Is it out of our reach to go deeper into space? Will I ever be sipping tea in deep space? Well, I want to answer yes to this. I want to say it is completely out of human reach. Things like warp speed and hyperspace are just not realistically on the drawing board until humans can harness at least fusion, perhaps antimatter, or other means of power. The power necessary to do the sorts of things you see in sci-fi are just beyond our current chemical propulsion methods. We just don't have a way to do it. I would argue that it's a good thing for sci-fi movies to get our hopes up, because if not, who will ever do the work necessary to get from where we are now to where we need to be? It often actually leads to actual inventions. No one in Star Trek in the 60s thought that mobile communicators would be possible, and today they are the most mundane thing that every single person walks around with in their pocket, so you never know. However, the distance to Proxima Centauri, our very closest next star, is about 4.25 light years. So 25.25 trillion miles or so, give or take. These are the sun's closest neighbors. Now, there's been a lot of interest in Proxima Centauri, which is the closest star, because it's thought that there might be some habitable worlds. And in fact, there's been a lot of studies into that. So that's kind of interesting. The fastest ever human-made spaceship is the Parker Solar Probe, which hasn't got there yet, but will in fact increase as it swings around the sun the last time, up to 430,000 miles per hour. Now, nothing travels in space at a constant rate. Remember, there's always gravity tugging one way, tugging in another. So this is the fastest, and it's going to be because of a slingshot around the sun, getting very close to the sun, which is going to speed it up. So if this is the fastest spacecraft we've ever gone, and we know what the closest star is, let's do the maths. So, are we there yet? 4 light years is about 25 trillion miles and a quarter. Traveling at 430,000 miles per hour would take you 58 million hours divided by 870 hours in a year, 8,760 hours in a year, blah, blah, blah. It would take 6,636 years to get to the next closest star, the very first closest star, at the fastest we've ever been able to travel. And certainly a human would not survive that sort of acceleration anyways. That would not be good for the human body. Think about how far back that is in time. 6,636 years. That's about the time we started this class. That's about the time period where we first started with the Sumerians. So that's a while ago. Now, if we sent a generational ship to go there right now, assuming that you're okay with condemning not just the crew that volunteered, but every single one of their descendants for hundreds of generations that did not volunteer, to live their entire lives on a spaceship and never know Earth. Now, if you're okay with all of that, you have to ask, when they did arrive at 6,000 years later, would what arrived be human still? And would they have any interest whatsoever in fulfilling the original mission that some crazy people that they don't even believe existed anymore gave them? It's hard to say. There have been several recent theoretical concepts floated that can go faster, but they all rely on things that we just don't have right now. So, hard to say. but not soon. Beyond that, and more to the point of your question, there are many bad impacts on the human body, as we saw in week 5. You can see the NASA Human Body in Space link there. Prolonged exposure to low gravity weakens the human skeletal system. You don't feel it because humans evolved on this planet, but the weight of the atmosphere and the gravity here is a lot heavier than you think. 14.7 pounds of air at sea level above you, to be exact. Your bones and muscles work to overcome Earth's gravity and atmosphere every moment of your life. They're constantly being exercised. And it currently remakes itself. Your body remakes itself as you grow. So your skeleton is a brand new skeleton. About every 10 years, it's completely remade. Many of your body parts remake themselves much quicker. Here's a list on the left. Red blood cells make their journey through the bloodstream with a lifetime of about 4 months. So if you connect that with the fact that there's about 3 times 10 to the 13th red blood cells, you can infer that about 100 million new red blood cells are being formed in your body every minute. Now that's pretty impressive. So when you take yourself out of Earth's gravity and put it in space, obviously a lot of things are different, and it completely changes the way your body reacts. We've never been in space longer than a year, and always with the idea of returning to Earth. But that would probably not be the case if we were actually outbound on a generational ship. No one has yet volunteered for the experiment to spend the rest of their life in space and never return to the Earth's surface and just see what happens. Maybe even have children in space and see what happens. There are moral implications here for some, for sure. One early Russian scientist hypothesized that human limbs might turn from bone to more like a cartilage, and humans might end up being closer to a 4-tentacled octopus in space if they lasted long enough. And in fact, there was a recent paper suggesting that octopi were once originally aliens. You can check it out there. The truth is, we simply don't have enough information. National space agencies would never do this sort of experiment. Bring them home is part of the deal. But when most of the Euros came to settle the Americas, it was a one-way trip. When they expanded west, it wasn't with the idea of coming back. One-way trips, often sponsored by wealthy private individuals and then given the backing of either governments or scientific institutions, is the primary way exploration has happened across the globe almost throughout history. So this is really not that uncommon. There are many, many historical analogs that bear this out. And this brings us back to the idea of public-private commercial partnerships. Often the best way is when they both work together. But all that said, I'm going to answer to your question, no. It is not impossible. It is not out of reach. We can do this, and in fact we must do this. Yes, there are many hurdles, but there will also be many breakthroughs along the way. Every journey starts with the first steps, and we must take them sooner rather than later. There are people all over the world right now, working on this. Many have spent their entire lives doing it, knowing they will never see the results of their work, such as this recent paper, computing the optimal population mix needed for a multi-generational ship to Proxima. The reason is simple. Every one of them knows that remaining a single species planet is asking for extinction. Even if we eliminate all of the possible human-induced causes, like nuclear war, or global warming, or AI, or nanotechnology, or genetic manipulation, or stupidity, a bad coronal mass ejection will come our way one day, or gamma ray burst, or a large comet or asteroid will impact one day. It's happened many, many times before. It's going to happen again, and not much is going to matter if the surface is molten. Or who knows what we don't even know about yet. Or perhaps an angry alien that thinks we taste really good with butter. Who knows? The problem is, of course, the likelihood of any of these things happening in the next 4 years is very small. So every single world leader can pass it on to the next guy saying, we'll wait till the next, yeah, we're good. We can't spend money on that sort of crazy stuff. But of course, if we wait until the problem arrives, it's far too late. And so it goes. All right. Next question. Space debris. How do we account for space debris when we launch in a rocket or inhabit a station like the ISS? Well, this is the cupola window, the window on the ISS, the big sort of picture window there. I don't know about you, but seeing this would make me really uncomfortable. Fortunately, it's quadruple paned, but the size of the object that impacted this glass was estimated to be about 1/1000th of a millimeter. I don't really want to think about what would happen if that would hit the spacesuit of an astronaut on an EVA, but realistically, it is only a matter of time before that happens. There's just so much debris up there. Here's another impact crater. This one was on the windshield of the Space Shuttle Challenger STS-7 following a collision with a paint chip at 11 kilometers per second. The entire window had to be replaced when they came back down. Imagine if it had been a pebble or a small rock, just a tiny fraction of an asteroid or comet or meteor, just so much worse. People have known about this problem for a long time. Believe it or not, out of sight, out of mind, very few people thought about what was going to become of all that junk. Everyone was so focused on getting the stuff into space that it led to, no surprise here, a lot of really bad short-term decisions. Like Project Westford, for example, that scattered 500 million copper needles into orbit to create an artificial ionosphere just in case there was a disruption. Of course, there never was a disruption, and the whole thing, and the money, and the contribution to orbital pollution that still exists today, all because a few dudes at MIT went absolutely nuts, and nobody stopped them. And of course, it had nothing to do with funding. This is a computer-generated image of the objects in Earth that are currently being tracked. 95% of them are orbital debris, non-functional satellites. 95%. Space is really hard on electronics. Most satellites last for 5 to 10 years, maybe 20. For the past 25 years, the industry global standard worldwide has been boost it to a higher orbit so it won't get in the way of the really valuable ones, and we'll let the next generation figure it out. I wish I was joking. The graveyard orbit is anything above 300 kilometers. It's above GEO with a period longer than 24 hours. So there's that. But the low Earth orbit, the ones that are much closer, there's another problem. There's a principle called Kessler syndrome, after NASA scientist Donald Kessler, who said that there will come a point when it gets so crowded that it will start a cascade. And you can see on the right, one hits, creates a domino effect, then that hits 3, and then that hits 9. And then it could be an entire generation or longer before all of that material falls out of the out of orbit and into the atmosphere. Debris left in orbits below 370 miles, really close in, will fall back to Earth in just a couple of years. Altitudes higher up, orbital decay is measured in decades. Above 620 miles, which is 1,000 kilometers, orbital debris will continue circling the Earth for maybe a century or more. Geostationary orbit is at 22,000 miles up. It will be an awful long time before any of that sorts itself out automatically. What do you think might happen to our society if space was completely inaccessible for 3 generations? Just 3. Do you think your great-great-grandchildren will believe that we went to the moon, when there are people alive right now that were alive in 1969 that don't believe we went to the moon? Of course, if that wasn't bad enough, several militaries, including the US, the USSR, China, and India, have all performed at least one anti-satellite test. Some have done more than one. The US tested its first almost 60 years ago. The US countered in with space killer satellites. Rather than launching missiles, they had satellites that could. But those needed at least 2 orbits to sync with the target, and 2 orbits is 3 hours. And in a military theater, 3 hours is a long time. So in addition to using dedicated missiles, the major powers have also conducted research on high-powered lasers and other directed energy weapons for use against satellites. In 2008, the U.S. used a missile to destroy and intercept a ballistic, the U.S. Navy used a missile to destroy an old reconnaissance satellite. Wow, that was difficult to say. In 2019, India did an anti-satellite test. In 2007, China did one. So all of these debris fields just keep growing and growing and growing. Now, this is just nations. Heaven forbid there's a terrorist. Anyone with the ability to launch a rocket could fill the nose cone with 10,000 ball bearings and let them loose in a busy orbit traveling opposite the spin of the Earth. And there is very little that could be done to stop that. But because it's a major problem, in desperate need of a solution, there are many companies right now all around the world that are working on real solutions to this problem. Because I think it has to be solved in this generation, or it's going to get a lot worse. I should mention, they are all hiring. All right, question 4. Nothing in particular, but I would like to use a telescope to view the night sky and the stars. I would like to learn more about what to see and where to look to see different things. I really wish we could have done more of this. I tried to give a bit of that experience in the observation assignment. And I really wish we could have got some time on a professional telescope. And we can, because we can do it distance. There are some observatories that allow you to do that. But there just wasn't time. And because it's a history-focused class instead of a science-focused class, I kind of had to keep the focus on the history, so that really was never possible. But almost every city I have lived in across the U.S. has had some sort of local astronomy group, and they are the best resource in the world. Every one of them has folks that know more about the night sky than I ever will. At OSU, I would direct you to the astronomy club in the physics department, and you can get a hold of them there. 2 more. Number 5 is spin-offs. I would like to learn more about gains in technology that were made for space. So several of you wanted to know more about spin-offs, and I hope that week 8's assignment on this directly at least helps see some of the breadth of contributions that now underpin so much of modern society that we take for granted. Sorry. And I want to since we've already talked about spin-offs, I just want to talk about one particular one. In this case, it's aerogel. When I was at JPO for my summer internship, that was completely supposed to be about my volcano research and was on day 1 completely converted over to working on the Cassini mission. Completely my choice, by the way. I was grateful for the chance. Anyhow, all of us raw cattle, as I overheard one of the scientists call out. Side note, it was sad too, because I had really wanted to meet the asshole. After that, but this story's not about him. Anyway, the cattle all piled into the storeroom. And across the hall was this guy, the man who invented aerogel. Perhaps invented is too strong of a word. Peter So was the JPL scientist that revolutionized the use of aerogel for space missions. He was the deputy PI on Stardust, and that was the mission that first captured samples of a comet. And they had a big tennis racket full of aerogel that popped up, and they flew right through it, and it captured the particles as it went through. One day he calls me over into his office, and he gave me a tiny piece of aerogel. In fact, I still have it. It was the absolute highlight of my time at JPO, because he was just being nice. I later heard that his lab at JPO was being dismantled and taken down and taken away from him because they needed to make space for another project. It broke my heart. But it happens all the time. Space is limited, and there are no shortage of young scientists moving up and working on new projects. And if you're a scientist, you're only as valuable as the project you're working on. And maybe your next project. For many, this means bouncing from mission to mission. I know some people that are planning 10 years ahead which mission they're going to be working on when this one's done. For some, it means they'll only ever get to work on one space mission. To his credit, Dr. So said he always felt like he had had the opportunity to live an amazing dream. Where else could you have done that? And how could he ever be bitter about being able to do that? And I tell this story to make a point. History is not just a wheel. It's kind of a grindstone. Very, very, very few people, no matter how important their contributions or their work are, will be remembered, even 2 generations later. If you have visions of personal glory, this is probably not the life for you. But just like the astronomers of old, the work remains, and its importance will only grow. In this case, if you created a 1-inch thick layer of aerogel, you could warm an igloo on the North Pole with only body heat. Fiberglass insulation in your house is R3.5. You might be able to get up to a little bit more than that. R8. Aerogel is R40. Oh, and it can also take a direct point-blank shot from a flamethrower.
The blanket, just 1 centimeter away, will be my hand on the back side of the blanket. Okay. Okay. I'm ready. Go.
Please don't try this at home. Aerogel.
Going hard?
Pretty amazing stuff.
Come in. I don't feel any heat.
All right. How do I move on? There we go.
Alrighty. Well, one more question. Aliens. Many of you asked about aliens. And it's a good question. It is. Sadly, it's one without a lot of good answers. But rather than give away what's coming, I will promise that we go into this subject from multiple different angles in week 10. That's what's coming next. This week is somewhat of a rabbit hole. The further you look, the stranger it gets, and yet some of it can be quite compelling. There are many people who have made this quest their entire life's work, and thus far not a single one of them has been rewarded with anything other than disappointment. But our tech is infantile, so you never know. This week we will calculate the Drake equation, which is the thought exercise into the likelihood of alien existence in the Milky Way, and we'll use current scientific estimates to find a result. And then you will compose a message for ET, Remember, no spoken or written language can be used in your message. Symbology is okay though. Pictures are fine. For now, I'm going to leave it there. I've probably rambled on for far too long anyways. I'm happy to talk specifics on this topic on the forum if there's something that's not answered in this week's readings and lectures. So that just brings us to your presentations. Thanks again for posting your questions. I try to take student interest really seriously and make sure that we can talk about the things that you're interested in. As I said from the beginning, I thought this might be helpful for you to see a presentation that models some of the things you should be doing. Mostly if you make a claim, post a source. If you refer to an image, post a source. If there's a good place for more info, post a source. You get the idea. This week, you will each be presenting your research to each other. I'm going to call it the Space History Conference. It won't actually be a conference this year, but maybe someday. Let's hope. I look forward to seeing your presentations on your research. Hopefully you've had plenty of time this week to get all of your information compiled, your sources ready, your arguments and your thesis set, and your writing started. Please give your peers as much feedback on their results, on their research and thesis as you're comfortable with. This is the last time that each of you will get feedback other than the automated feedback from Turnitin, so be sure to help your neighbors as much as you can. I look forward to hearing them, and thanks for listening. Cheers.